This video lesson is all about Le Chatelier's principle, and it's at the tail end of the equilibrium chapter. Le Chatelier's principle is very applicable to real-world chemistry situations. This is specifically involved with mentioning or messing around with a system at equilibrium. This topic is of particular interest to anybody who wants to do chemistry in the future in industry or chemical engineering. Basically, the concept is that Le Chatelier's principle, you're looking at a system at equilibrium. The basic concept is if a reaction is at equilibrium and is disturbed by a change in concentration, pressure, or temperature, the reaction will react to relieve the stress put on the reaction. It's important to keep in mind that a reaction wants to keep its Kc constant. Now, for a moment in time, the reaction will not keep its Kc value, but it will reestablish Kc by either reacting to produce more products and reduce the amount of reactants, or respond to produce more reactants and produce less products. And so the reaction is always striving to get back to Kc, but when equilibrium is adjusted, the reaction for a moment in time will not be at equilibrium, but then will reestablish equilibrium after a certain period of time. Now, the terminology that we use when discussing stress put on a situation at equilibrium is the reaction responds by either going right or going left. And going right, what we mean is it produces more products. When a reaction goes right, what we really mean is that some of the products are produced and some of the reactants are minimized or are used up. And what that means is that the reaction tries to reestablish equilibrium by making the K expression, which is products over reactants. By producing more products and minimizing the reactants, Kc reestablishes. And so this is what happens when stress is put on the reactant side of a reaction. The reaction responds by producing more products and reducing the reactants. Now, on the other hand, if a reaction is said to be going left, it actually what it does is minimize or reduce the products and increase the reactants to try and get Kc to get smaller. This is what happens when a reaction has put stress on the right side of the reaction and Kc tries to reestablish at a lower number. Now, the first scenario we're going to look at is a situation where concentration of either the reactants or the products has been affected. The reaction that I'm going to use in my examples here today is this one, the production of NH3 from the two gases N2 and H2. The balanced chemical reaction is shown. Now, if you want to change the concentration, you can either add or subtract reactants or add or subtract products, and each one is going to put a stress on this reaction in its own individual way. Now, let's just say, for the sake of easy numbers, that this reaction has a Kc value of 10, which means that you have its products favored and you have 10 products for every one reactant. Now, you can put stress on this reaction by adding some of the reactant, maybe some N2 gas to the chamber, and for a moment in time, Q is going to be less than 10. Maybe you add more reactant, and all of a sudden the ratio is 10 over 2 or 5. So immediately the Q quotient, or the moment in time, the equilibrium is adjusted. Now, reaction wants to be at 10, so what's going to happen is this reaction is going to shift to the right to try and minimize the reactants and more products so that it can reestablish in the ratio of 10 over 1. By putting something like N2 or H2 into the reaction, it forces it to the right. Now, you can force it back to the left if you want to say maybe put some NH3 in. Now, NH3 is going to increase the concentration of the product side, and the reaction is going to proceed back to the left. It's going to proceed back to the left. It's going to try and create more reactants and minimize the amount of products. Now, in this case, when I add NH3, maybe it's originally 10 over 1, but by adding products, you're now 20 over 1, which is 20. Now, that's high compared to where it wants to be. So what's going to happen is the products go down, the reactants go up to try and make that ratio of products over reactants to equal 10 over 1. And that's what we mean by when we say that the reaction shifts to alleviate the stress on the system, it tries to reestablish the proper ratio of products over reactants. So putting stress on the right-hand side forces equilibrium left, and putting stress on the left-hand side forces equilibrium to the right. Now it's important to note that just adding reactants or adding products moves the reaction, so does removal of products. If you remove some of the products, you're going to drag the reaction along with it. And the reaction is going to try and force the production of more products. And so there's two ways to make a reaction go right. Either remove some of the products or add some reactants. Now the same can be true about the other side. If you want to force a reaction left, you can add product or remove some of the reactants away, and it's going to drag the reaction back towards the left. So you're either pushing the reaction to the right or pulling it to the left, or pushing it left or pulling it right. Think of these reactants and products on a string, and you're either moving them right or left depending on what you want to do or what the stress that was put in on the reaction itself. The next stress we're going to talk about is a change in volume/pressure. As we learn in the gas laws unit, as volume is increased, pressure goes down. Basically, you're expanding the volume of the reaction and the pressure inside the chamber decreases. It's Boyle's law. Conversely, if volume goes down, pressure goes up. So you could change the pressure or the volume in these reactions to put stress on the system. Now this is also important to note that this only works, changing volume or pressure only works when you have gaseous equilibria. The most important thing to look at when you're discussing changing volume or pressure and its stress on a reaction is identifying how many moles of gas are on each side. If you look on the left-hand side, there are 4 moles of gas total, 1 mole of N2 and 3 moles of H2. On the right-hand side, there's 2 moles of gas, just the one product, 2 moles of gas. So we have an imbalance of gaseous moles on the reactant side and product side. Now this is easy to confuse, so pay close attention, but basically what you're looking at is trying to put stress on one side or the other. Now it's important to note that if the moles of gas are equal, then changing volume or pressure has no effect. But in this case, it's obviously clear that one side has more moles of gas than the other, so this is definitely going to be affected by change in pressure or volume. And let's just talk about changing pressure by decreasing volume. So the pressure increases, and what's going to happen, it's going to squeeze one side of the reaction that has more moles. So it's going to force the reaction towards the side with less moles. Conversely, if you decrease the pressure, it's going to cause the reaction to shift to the left in this case, because it's going to want to relieve the pressure by forcing more moles of gas to be produced, so it's going to shift to the side that has more moles. Increasing the pressure forces the reaction towards the side with less moles of gas, so that's in red. I squeeze the reactants down, and it's going to force the reaction to shift to the right towards the products. Now, on the opposite is true. By decreasing the pressure, you're going to force the reaction towards the side with more moles. So if you expand the volume, you decrease the pressure, and the reaction is going to shift towards the side with more moles of gas, in blue up here, so that the gas is produced to fill the empty space. By increasing the volume and decreasing the pressure, the gas wants to shift towards the side with more moles so that it can fill in that empty void. This picture shows a pretty good pictorial representation of what's happening when pressure is increasing or decreasing, and the size of the box represents the volume. So we've got volume, 3 different volumes here. Let's treat the middle one at equilibrium. So at equilibrium, we've got this ratio of gaseous moles. We've got 2 on the left and 1 on the right. So let's take a look at going to the right. So we increase the volume and decrease the pressure, and the reaction is going to adjust by forcing more moles of A to be produced, which, as we talked about on the last slide, when pressure decreases, the reaction is forced to the side where more moles of gas. Now in these 2 examples that I've shown you, the more moles of gas is the reactant side. It's not always going to be the reactant side. It's going to be the side where there are more moles of gas compared to the other. So we've got 2 to 1, which is why you'll see lots of red dots or A's. A increases and B decreases. Now go the other direction. If you squeeze the gas, compress it down into a smaller volume by increasing the pressure, what happens is that you force the reaction back to the right, minimizing the amount of A and increasing the amount of B, because 1 mole of B takes up half the volume as one or 2 moles of A. So to compare the two, it makes sense that a reaction reduces its volume, it wants to minimize the pressure by forcing the reaction to produce less moles of gas. This reaction happens once, it takes up 2 A's and produces 1 B, so it decreases by a factor of 1/2. Now if the reaction was flipped where you had 1 A and 2 times B, then the reaction is going to adjust once again according to which side of the reaction has more moles of gas on it. Finally, we're going to take a look at the effects that changing in temperature have on shifting equilibrium. I'm going to use 2 general reactions here. One is an exothermic reaction, and remember when exothermic reactions are written out, we either have the delta H as a negative value, or we can add it as heat to the product side. Now if it's an endothermic reaction, it'll be listed as delta H as positive energy in, or it'll be listed on the reactant side. Now what I like to do when I'm looking at changes in temperature is treat the heat as a physical reactant or product. Treat it as if it were a molecule on the reactant side or the product side. And it seems to act, in that case, just like changing concentration, but instead of changing concentration, you're changing heat. Now take, for example, the exothermic reaction right here. Now if you add heat by performing this reaction at high temperatures, so the reaction produces heat and the reaction is at a high temperature inside a chamber where heat is added, the heat is going to force the reaction to go back to the left or back towards the reactant side. Now on the other hand, if you do an endothermic reaction in the presence of heat or at high temperature, it's going to act as a reactant and force the reaction towards the right or towards the products. Now on the other hand, take heat away of an exothermic reaction, perform this exothermic reaction in a cool environment, and you'll force equilibrium to the right. So you're basically removing the heat that's being produced in a cool environment will absorb the heat and drag the products towards it, drag the reactants towards the right side. Whereas if you perform an endothermic reaction in a cool environment, you're removing the heat. The heat is needed for the reaction to proceed to the right, but you're keeping the heat from reacting, so you're going to drag the reaction back towards the left. So you need to know, first of all, where's the heat? Is it a reactant or product? And then decide, is the heat forcing the reaction left or right, depending on where the heat is placed in the system at equilibrium. Now finally, how does a catalyst affect a system at equilibrium? Catalysts have no effect on the equilibrium constants or expressions. You can have 2 reactions, one that's catalyzed and one that's not catalyzed, A to B uncatalyzed and A catalyzed with X to B, and both will reach equilibrium Kc at the same number, 10 for example. The difference though is that catalysts affect the speed only, and they affect the speed at which equilibrium is established. Take a look at the 2 pictures up here. So you've got the one on the left that shows 2 reactions, a green reaction and a purple reaction. Now this looks a lot like the potential energy profile from last chapter. Notice the green is the catalyzed reaction, and so you've got activation energy achieved at a lower energy threshold right here. So it basically forms an alternate pathway for a reaction to proceed from A to B. But the ratio of products to reactants is unaffected. You still have this much product and you still have this much reactant. Now if you compare that to over here, if you don't look at the potential energy profile but rather look at the kinetics concentration versus time curve, what you observe is that the reaction concentration, this is the products being produced, eventually reach a point of equilibrium. The purple line and the green line both eventually reach the same point but never exceed that. That's how what B is at equilibrium. It means you don't produce more product with the catalyst. It's just that in green, the catalyzed reaction has a steeper slope initially, so it reaches equilibrium faster. But it has no effect on the catalyzed or uncatalyzed, have no effect on the K constant itself, because K is still determined on concentration of B over A, not the speed at which the reaction reaches equilibrium. This reaction up above is at equilibrium. This is from number 2 in the AP FRQs, and all of these questions pertain to changing or putting stress on this reaction and seeing what happens. So we need to talk about whether or not the reactants, whether or not the CO2 in the container will increase, decrease, or stay the same. So we're keying in on not the CO2, but the CO. So A, does the addition of H2 added to the equilibrium mixture at a constant volume, does it make the CO go up, go down, or remain the same? So H2 is a product, and so is CO. And by adding a product to a system at equilibrium, it'll force the reactants to force a reaction back to the left, which in turn will make CO go down because the reaction is forced to the left, producing more reactants and reducing the number of products. So CO decreases in situation A. In B, the temperature of the equilibrium mixture is increased at constant volume. Now, as I mentioned before, I like to add the heat in to one side or the other to tell me whether or not it's a reactant or product. And since it's a positive value, it's a reactant. Now, increasing the temperature will essentially add heat to an endothermic reaction, which is like adding a reactant to this system at equilibrium, which will force equilibrium to the right. And as a result, the concentration of CO will increase. So will the concentration of H2, but we don't really care about that. It just asks what happens to the CO when the reaction is stressed by temperature. Now finally, the reaction is going to be stressed by changing in volume. Now it doesn't say it specifically, but when the volume is decreased, the pressure is increased, and that's what you're focusing on, is the pressure and how it affects the reaction at equilibrium. Make note of the moles of gas on the left-hand side and the right-hand side. I have 1 mole of gas on the left and 2 moles of gas on the right. Notice the carbon is solid, so it doesn't count as a gaseous reactant or product. So I just have 1 on the left, 2 on the right. And if you remember from a previous slide, when pressure increases, it squeezes the side of the reaction that has more moles to try and produce less moles. So it's going to force the reaction towards the side with less moles, which is to the left. And when it does that, the concentration of CO will go down because the reaction is trying to produce more reactants and minimize the amount of products produced. Finally, letter D, the graphite pellets are pulverized. Now the graphite pellets, as they mention right here in the first sentence, is basically the solid carbon. Now when it pulverizes, it becomes smaller, and that's okay, but this goes to our conversation on homogeneous and heterogeneous equilibrium. Remember, Kc or Kp only are affected by things that are in a gas or in aqueous, and if they are solids or liquids, they're not included as part of the equilibrium expression. So I can write out the equilibrium expression of the reaction up above. Notice at no point does carbon make its way into the equilibrium expression. So it doesn't matter if you pulverize it, add a bunch to it, subtract a bunch. Doing anything to the graphite has no effect on equilibrium whatsoever, and so you don't have any CO increasing or decreasing. It has no effect whatsoever.